So, in review, here is the definition of conditional probability with which we ended the previous video. The conditional probability of any sentence phi given psi equals the unconditional probability of their conjunction, phi and psi, over the unconditional probability of psi, which is the sentence being conditioned on. So let us now work through some examples to see how this definition works. So here is the first example, and this is similar but not identical to an example from the very first uh, chapter of the textbook. This is a simple version of that kind of example. So suppose you're on a game show with three doors, A, B, and C. The doors are closed and you don't know what's behind them, but you do know that one of these three doors, A, B, or C, has a prize behind it. And you have no idea which one of these doors is more likely to have the prize. The prize is put randomly behind one of the three doors. So where A, B, and C stand for the claims that the prize is behind that door. So A means the prize is behind door A, B means the prize is behind door B, and C that the prize is behind door C. Because you have absolutely no idea which door has the prize behind it, your unconditional probabilities in each of A, B, and C is the same. It's 1/3 for each. Because you know that the prize has to be behind one of them, but you do not have any idea which. So you split 100% probabilities three ways between them equally. So I want you to then suppose that the host, for whatever reason, perhaps they're being kind, opens door C. And you look behind door C and you realize there is no prize. So now, given that door C has been opened and there's no prize from it, we can ask about what the new probabilities that the prizes behind door A and B are, given that we know it's not behind door C. That is, we can ask about the probability of A and B uh, conditional upon the prize not being behind door C. So what is the probability that the prize is behind door A, say, given that it's not behind door C? So take a moment to think of what the intuitive answer to this question is before we dive into the formal details. So again, we start out thinking that the prize has equal chance of being behind three doors. Then we learn that it's not behind door C. So what becomes the probability that it's behind door A, say, given that it's not behind door C? Now the intuitive answer is that it is 1/2. There, given that it's not behind door C, now the probability that it's behind A is 1/2 because the full probability is now split equally between A and B. But now what we can do now is use our definition of conditional probability to calculate 1/2. So let us look at the formal answer and verify that it lines up with the correct intuitive answer. So here is a calculation, and let me walk through this calculation with you. So first, we write what we're wondering about is what is the probability of A that the prize is behind door A, given that it's not behind door C. Now this first step here, in this first identity claim, is simply an application of the definition of conditional probability. So the definition of conditional probability said that the probability of a sentence given another is equal to the probability of the conjunction of those two sentences over the probability of the sentence being conditioned on. So here we have simply applied the definition of conditional probability. So the probability that it's behind door A, given that it's not behind door C, is equal to the unconditional probability that it's behind door A and not C over the unconditional probability that it's not behind door C. Now, this next step is a little bit more advanced, and what it requires is understanding of certain logical equivalencies, and also given our understanding of the background assumptions about this problem. So let's start with the bottom. So one rule of probability, which we covered last week, is that if two sentences are logically equivalent, then they have the same probability. So if phi and psi are equivalent, if any two sentences are equivalent, then probability of one, you'll have to excuse this writing, I'll do better. So any two sentences, phi and psi, that are logically equivalent are such that the probability of one is the same as the probability of the other. So this is the rule which we are appealing to in this step. So as it turns out, not C is logically equivalent to A or B. Now why is that? That's because we're assuming, as a background setup for this question, that the prize has to be behind one of these three doors. So we're assuming that either A or B or C has to be true. So therefore, if C is false, then either A or B has to be true. And if A or B is true, that is, if the prize is behind either door A or it's behind B, then it's not behind C, because we're assuming that there's only one prize behind one of the doors. So with understanding the setup, we understand that not C is equivalent to A or B. And therefore, they have, according to the rule which was introduced in the last lecture, therefore they have the same probability. And therefore, we can swap out their probabilities by and retain identity. Okay, so that is how the first part of this step works. We replace the probability of not C in the denominator with the probability of A or B, because these two sentences, not C on the one hand and A or B, are equivalent. But now let's look at the numerator. How is it that we swap out the probability of A and not C with the probability of A? Well, the reason for that is the same reason, this rule here, which is that A and not C is actually equivalent to A. Now, why is that? That's because not C is equivalent to A or B. And because not C is equivalent to A or B, the conjunction A and not C is equivalent to A. So since, again, not C is equivalent to A or B, we can rewrite this conjunction of A and not C as A and A or B. So let me do that. So A and not C is equivalent to A and A or B because not C is equivalent to A or B. And now, hopefully, you can see intuitively how A and A or B is equivalent to A. So you could verify this with a truth table, but also hopefully you can see intuitively why, because suppose, for instance, that A and A or B is true. It must therefore be that A is true. So this first sentence entails a second. And also, suppose that A is true. Therefore, it must be that both A is true, which is the assumption, and also that this disjunction A or B is true, because the disjunction is true when at least one of the disjuncts is true, and we're assuming A is true. So these two sentences are equivalent. So that is why we're able to replace these probabilities with these ones here. So the probability of A given not C is ultimately equal to the probability of A over the probability of A or B. And we have managed to get that result by applying this rule that logically equivalent sentences have the same probability, and then noting some of the important logical equivalencies given how we've set up the example. So now that we know that this formula here gives us the conditional probability of A on not C, the next step we do is we don't have to change the probability of A to anything else because we know that from the example. In fact, we know that the unconditional probability that the prize is behind A, door A, is 1/3. But now, to figure out the denominator, what we note is that A and B are mutually exclusive because we assume that the prize is only behind a single door. So because A and B are mutually exclusive, we calculate the probability of their disjunction by summing up the probability of the disjuncts, and that was another of the rules given on Monday. That was the rule which said when you have a disjunction with mutually exclusive disjuncts, the probability of that disjunction is equal to the sum of the disjuncts. So that is how we arrive at this third step. And now we just fill in from the setup what the unconditional probabilities of A and B are. So again, we know from the very beginning of the game show that the unconditional probability that the prize is behind one of the doors is 1/3. So here we simply, so the probability that the prize is behind A is 1/3, and the probability that the prize is behind A is 1/3 again, so we have two of the same terms, and the probability that it's behind door B is also 1/3. So simplifying, we get the answer 1/2, and that is exactly the intuitive answer which we began with. All right, so here is a final gloss on the calculation we just did. So before any door was opened, A had a 1/3 probability out of 1 of having a prize behind it because A was one of 3 equally probable doors that the prize could have been behind. And then, now that C is shown to be empty or conditional on not C, A has 1/3 out of 2/3 probability. So here we see this in the penultimate step of the calculation that the probability of A given not C is 1/3 over 2/3. So after the door C is open and we know that it's empty, A has 1/3 out of 2/3 probability of having the prize behind it, and that is just 1/2. So, and I just want to stress one thing, which is that, and also I mentioned this last class, that these sentence letters A, B, and C are crucially here assumed to stand in logical relations. So the way we so it's crucial to doing these calculations and being able to swap, replace, or substitute the probabilities of logically equivalent sentences. It's crucial that you realize that given our setup, we're assuming that these sentence letters have logical relations. So we're assuming that, for instance, the prize has to be behind at least one of A, B, and C, and not more than one. And understanding that setup is crucial to seeing how, for instance, the probability of not C is the same as the probability of A or B. So here is another example. Suppose I roll a fair 6-sided die. So you can't see the result, but I can. So for instance, I rolled the die I rolled it behind a screen, and you can't see on my side of the screen. And now I tell you that the dice came up as an even number. So you learn that the die is rolled an even number. So now you might ask, what's the probability that it's a high number, i.e. a 4, 5, or a 6, given that it's even? So suppose that you believe me that it's even. Now you might ask, what's the probability that it's a high number, given that the dice rolled on an even number? The intuitive answer to this question is 2/3. That's because if you think of all the even numbers, 2, 4, and 6, 2 out of 3 of those even numbers that it could have landed on. So again, the even numbers that the dice could have landed on are 2, 4, and 6. And 2 out of those 3 even numbers that it could have landed on are high, i.e. 4 is high and 6 is high. And the final even number, 2, is not. So given that it's rolled even, there are 2 out of 3 ways of it landing high. So that means intuitively that the probability that it's a high number, a 4, 5, or a 6, given that it's even, is 2/3. So now we can do a similar calculation to the one we just did to show this. So let's do this calculation. So the very first step is we write out formally the conditional probability that we're interested in. And in this case, we're interested in the probability of it landing high, given that it landed even. And simply in applying the definition of conditional probability, we get that the conditional probability of H on E equals the unconditional probability of the conjunction H and E over the probability of E. So what is this conjunction here, H and E? Well, that is just the numbers that it could land on that are both high and even. And the two numbers that are both high and even are 4 and 6. So the proposition that it lands high and it lands even is equivalent to the proposition that it either lands on a 4 or it lands on a 6. So these numerals here inside of the probability operator, which I'm disjoining, these are not standing for numbers. These are standing for the propositions that the die lands 4, say, or the die lands 6. So this is just shorthand for full propositions. So the probability that the die lands high and even is equal to the probability that it lands on a 4 or it lands on a 6. So that's why the numerator can be changed to the probability of landing 4 or landing 6. And now the probability of the die landing even is the same as the probability of it landing a 2 on a 2, of it landing on a 4, or of it landing on a 6. So these are the 3 ways that the die can land even. So this step here, after we've unpacked the conditional probability given its definition, is simply by rewriting these probabilities with logic in logically equivalent ways. Now, very similar to above, what we notice is that these different ways, the die landing 4 or the die landing 6, are mutually exclusive. That is, the die cannot land both 4 and 6. So once we recognize that, we see that we can apply the rule for calculating disjunctions of mutually exclusive sentences. So because the die landing 4 and the die landing 6 are mutually exclusive, the probability that it lands 4 or that it lands 6 is equal to the probability that it lands 4 plus the probability that it lands 6. And similarly, whether it lands 2, 4, or 6 are mutually exclusive, so we simply sum up the individual probabilities of those mutually exclusive disjuncts. And now, given the setup, we can fill in these probabilities because we know that we're rolling a normal fair die. So the probability of each of these things is simply 1/6. So we simply put in the particular numbers that each of these outcomes has as their probability. So we have 1/6 plus 1/6 over 1/6 plus 1/6 plus 1/6, which is 2/3, which is the intuitive answer. So another way to gloss this is that the probability of it landing heads given even is 2/6 over 3/6, which is 2/3. That is to say that there are two ways out of three of the die landing high given that it's landed even. So out of all the ways that the die can land even, there's two ways of the die landing high, and each of these has equal probability, so it simplifies to 2/3. Now, here is a visualization of what is going on behind the definition of conditional probability that will help us see what we just did in the last two calculations. So I want you to imagine that the space that A's circle here takes up is the amount of probability that A has. And I want you to similarly assume that the amount of space that B's circle, the blue circle, takes up is the amount of probability that B has. Now, as you can see, A and B's circle overlaps. What that means is that there is some probability that A and B are both true together. So in the last example, for instance, we wondered about the probability of H given E. So we wondered about the probability of the die landing high given that it landed even. And of course, it's possible for the die to land both high and even. That happens in the case where the die lands on a 4 or lands on a 6. So in this case, where A is H and B is E, there's some overlap between the possibilities of A and B. So this purple space here, this amount of area here, this purple area, is the amount of probability that A and B, the conjunction, has. So now visually, the probability of A given B is the amount of B's overall space that A and B takes up. That is, it's the probability of A given B is the proportion of B that is also A. And so to understand this bottom thing here with the addition, you can think of B's total space as being a combination of the part of B that is A and the rest of B which is not A, which is the blue part here. So if we add up the part of B that is also A and the part of B that is not A, the purple and the blue, we get all of B. And then if we consider just the purple, the part of B that's A, that is a probability of A and B. So the probability of A given B, the conditional probability of A on B, what that is visually is the proportion of B that is also A. Or another way of thinking about it is that how likely, given that we're in B, how likely is it that we're also in A? That is what the conditional probability of A given B represents. And that is why we look at how much of B's overall probability is also A. So now that we've done some calculations of conditional probabilities, let's look at a way in which conditional probabilities can be used to calculate other things, and specifically conjunctions. And we'll look at this in general and then apply it to the case we began with of Laplace's urns. So last class, I only told you how to calculate the probability of conjunctions when the probabilities of the conjuncts were independent. But what about when they are not? So we can often ask about the probability of a conjunction where the conjuncts are not independent of each other. So given our definition of conditional probability, we actually know how to do that. We know that the probability of a conjunction phi inside, no matter what relation phi and psi stand in, equals the probability of phi given psi times the probability of psi. Now, we do have to suppose that the probability of psi is greater than 0 to be able to apply this. But nonetheless, this way of calculating conjunctions applies whether or not the probability, whether or not phi is independent of psi or not. This is a way of calculating the probability of any conjunction, so long as psi has a greater than 0 probability. Now, you might ask, how is it? How is it that we know how to do this, given our definition of conditional probability? So let me show you on this whiteboard. So our definition of conditional probability was as follows. Probability of phi given psi equals the probability of phi and psi over the probability, sorry, that is awful, over the probability of psi. Now we simply divide each side of this equation by the probability of psi. And this is a simple mathematical trick, which I'm sure you've seen before. So if the probability of phi given psi equals the probability of phi and psi over the probability of psi, then the probability of phi given psi times the probability of psi equals the probability of phi and psi. And here is the probability of a conjunction with any two sentences as conjuncts. And to calculate that probability, we simply multiply the probability of psi times the probability of phi given psi. Now you might ask, how is this related to the rule which we saw in the previous class? So that rule said as follows. If phi and psi are independent, then the probability of their conjunction is simply the probability of phi times the probability of psi. So if phi and psi are independent, then the probability of their conjunction is simply gotten by multiplying their individual probabilities. But now, what does it mean for phi and psi to be independent? Well, we can give a simple account of that using the notion of conditional probability we have. So intuitively, independence means that the truth of one does not influence the truth of the other. So what that means is that if two sentences phi and psi are independent, then the probability of phi given psi will actually be the same as the probability of phi. So for two sentences to be independent is for the conditional probability of one given the other to be the same as its unconditional probability. That is, if phi is independent of psi, then phi's conditional probability on psi is the same as its unconditional probability. That is, learning psi or conditioning on psi does not change phi's probability, and that's what it means for two sentences to be independent of each other. So now, given this insight, let me write down again the general way which we just established of calculating conjunctions, regardless of whether they're independent, and see how we can relate that to the simple rule for when they are independent. So the general rule from a moment ago is that the probability of phi and psi, and excuse the rough writing. So, but the general rule is that the probability of phi and psi equals, in general, the probability of phi given psi times probability of, psi. So this was a rule that applies in general, regardless of whether phi and psi are independent. But then, if we know that phi and psi are independent, we know that the probability of phi given psi is the probability of phi. And that means that we can replace, in the case when phi and psi are independent, we can replace the probability of phi given psi with simply the probability of phi. And that's how we know that this more easier rule, which applies in the case of independent conjuncts, applies. So now let's return to the main thread. So now that we understand the definition of a conditional probability, we can now see how to calculate the probability of conjunctions even when the conjuncts are not independent. And in recognizing this, we're going to be able to give a better, more rigorous calculation of the example with Laplace's urns from the very beginning. So briefly, let's recall the setup from the beginning of the lecture. There are two urns in front of us. Urn 1 has 3 red marbles and 1 green marble. Urn 2 has 1 red marble and 3 green. What we're going to do is we're going to flip a coin to pick which urn to draw from, and then we'll draw twice with replacement from that urn. Now we ask, what is the probability of getting 2 reds, i.e. what is PR of RR, so reds in the first draw and reds in the second draw. So the first thing we do is we split the drawing of 2 reds exhaustively into mutually exclusive cases, and what we get from that is the following identity. The probability of drawing 2 reds equals the probability of drawing 2 reds and it being from urn 1 plus the probability of drawing 2 reds and it being from urn 2. So let me get out the pen. So because we know from the setup that we're going to flip a coin and it's going to land on either heads or tails, so that means that we're going to be drawing from either urn 1 or urn 2. So urn 1 or urn 2, one of these two things has to be true. We have to be either be drawing from urn 1 or 2, depending on how the coin lands. So that means is that the whether you draw 2 reds, which I'll write here, that is logically equivalent to the following disjunction. Two reds and urn 1, or 2 reds and urn 2. So whether you draw 2 reds is logically equivalent to it either being the case that you draw 2 reds from urn 1 or you draw 2 reds from urn 2. And that's what this disjunction here symbolizes. And now furthermore, because each of these disjuncts are mutually exclusive, that is, you can't be drawing from both urn 1 and urn 2, you have to be drawing from one or the other, the probability of the disjunction is equal to the sum of the probability of the disjuncts. So because, again, RR, so drawing 2 reds, is logically equivalent to either drawing 2 reds from urn 1 or drawing 2 reds from urn 2, we know that their probability is the same because of the rule which I gave you in the last lecture, that the probability of logically equivalent sentences is the same. And then, since we know that the probability of RR is the same as the probability of RR and U1 or RR and U2, we then furthermore apply the rule which says that the probability of this disjunction is equal to the sum of its disjuncts. So that is how we arrive at this equation here. Now, all we have to do to finish this calculation is calculate both of these probabilities of these two disjuncts, of the two conjunctions, RR and U1, and then the probability of the conjunction RR and U2. So we cannot, in this case, simply apply the rule which I introduced in the previous lecture. That rule for calculating conjunctions says that if the conjuncts are independent, then you simply multiply their probabilities. However, in this case, the conjuncts are not independent. The probability of drawing two reds actually depends on or is influenced by whether you're drawing from urn 1 or whether you're drawing from urn 2. That's because urn 1 and urn 2 have different distributions of red versus green marbles. So whether U1 is true does influence the probability of you drawing two red marbles. So that is to say that we cannot simply appeal to the rule for calculating conjunctions when with independent conjuncts, because these conjuncts are not independent. What we have to do is we have to appeal to our general rule here, which we derived from the definition of conditional probability. So applying that general rule, what we get is as follows. The probability of this conjunction is equal to the probability of the first conjunct given the second times the probability of the second, and the exact same thing for this other conjunction. So the probability of drawing two reds and it being from urn 1 equals the probability of drawing two reds given you're drawing from urn 1 times the probability of drawing from urn 1, and similar for urn 2. And as it turns out, we actually can easily fill these out because we know that the probability of drawing from urn 1 or urn 2 is 1/2, because that will be based on the flip of a fair coin. And then we know that the two draws are independent. The two draws of red are independent because we're drawing with replacement. So after the first draw, we will replace the marble we draw and then draw again. So both draws are the exact same. So we can now put all the pieces together into this. So this first identity was what we established at the beginning by splitting up two reds into exhaustive and mutually exclusive possibilities, which allowed us to calculate the probability of a disjunction in terms of summing up the probability of the two complex disjuncts. And then we apply the general rule for calculating conjunctions when, in this case, we need to apply the general rule because these are not independent conjuncts. And now we can simply fill out the probabilities. So again, we know that the probability of drawing from one urn or the other is 1/2. And we know because of the amount of red versus other marbles in the urn that the probability of drawing two red marbles in a row with replacement is just 3/4 times 3/4. And here, because we know there's only 1 out of 4 red marbles and each draw is independent, we simply multiply 1/4 times 1/4. So here we filled in all the particular numbers, and the rest is just a bit of mathematics. And we simplify and we get that the probability of getting two reds is 5/16, and that is the answer from the beginning. And here we've worked out in more detail. Now, if you look at figure 6.3 in the textbook, in chapter 6 of the textbook, you'll see there's a tree diagram that represents the reasoning behind this a bit more visually, which you can look at. If you do look at that, which will be helpful, just note that in that example, the marbles are black and white as opposed to red and green. But that's the only difference, and the rest is the same. And so you can see how this calculation corresponds to a tree diagram that's might be a bit more intuitive.